So this was the title I was given, and for those of you who are really fine scholars of the English language, it should really have been one biostatistician's answer, and I do not claim that it's more than one biostatistician's answer. And I'm going to risk insulting your intelligence for the first few minutes by taking you through something that I use when I'm teaching scientists their first course in statistics, and I have the advantage that they're postgraduate. I have the advantage that they're postgraduate scientists, so although they're statistically somewhat naive, they're scientifically sophisticated enough that they don't get upset if you talk a little bit outside their ostensible discipline. So I use this when I'm talking to biologists and the like. And most people can recognise that it's Isaac Newton, and I talk about an experiment we used to do in the first year physics undergraduate class, in which we gave students this rather crude piece of apparatus, in which we had an electromagnet, a stopwatch with a switch, a ball bearing, a calibrated ruler, and we just advised them to spend some time collecting data on how long it took for the ball to hit the bench and how that was affected by changing the height at which it had to fall. So nothing very complicated. And the one student's data looked like this. And the only pedagogical point here when you're teaching biologists is that I think most biologists presented with data like that would automatically use Excel to put a straight line through them. But anybody who knows any physics knows that although it would give you a very high R-squared, is wrong, because there's a physical law underlying the process that we're working on in the undergraduate lab, and that law tells us we need to do a transformation. And I do dwell a little bit on why we're going to transform to t equals root d, right? In other words, we're going to transform d rather than t, the answer being, of course, that t is the outcome rather than the input, and so we get something that really does look rather like a nice straight line, but unfortunately it doesn't go through the origin. And again, a moment's thought shows you that that's because what we're recording with that primitive apparatus is the time the ball takes to fall plus the reaction time of the person who has to then flip the switch. So then I can say, so now you're studying physiology, so that's all right, so you're with me now, okay? And now, of course, this is as good a data set you will ever find. I defy you to find a better one, in which the standard conditions of the linear regression model hold perfectly, and you can interpret not only the slope, which is the physical, it's gone now, right? Which is the physical quantity of interest. I will speak up and you will repair it. Thank you. Which is the physical quantity of interest, and incidentally you learn a bit about student reaction times at 2 p.m. on a Tuesday afternoon, and bingo. And that's just the linear model, and this sort of introduces you to what I think are probably now very well agreed statistical modelling principles, that models are just devices to answer questions. The minimal requirement of a statistical model is that, this is a phrase I got from David Cox, it's a typically cautious statistical phrase, not that I'm saying David's cautious, in which statistical models should be not demonstrably inconsistent with the data. That's not a very high bar to pass, but it's reminding you that if you want to show that your model fits the data, all you need is a very weak goodness of fit test, and you'll get the answer you want. The second thing, of course, is that if there is some well understood scientific mechanism, you should use that. And modulo those two things, try and keep life simple. Statisticians abhor complexity because they know that if you overfit within a data sample, you're likely to make poor out-of-sample predictions. And this may or may not have been in Mozart's mind when he had a little interlocution with his sponsor, the Emperor Joseph II, who couldn't play the pieces that Mozart had written for him. And so, if you want to sort of have a little simple metaphor for that, this is my science metaphor, which is that nature is at the apex, and fundamentally science is about trying to understand nature. It might be human nature, it might be biological, it might be physical, whatever. And scientists advance their knowledge of nature by two very different ways. Scientists advance theories in which they produce models, which are very often in very formal mathematical language, and borrowing a term from my friend Noel Cressy, I call this a process model because it's a model for the natural process that you're trying to study. Scientists also observe nature, either in the raw or in a controlled experiment, and they collect data. And very often when people talk about a statistical model, they're really just talking about models of the kind I've just illustrated, like regression models, which are just simple equations with independent errors. But of course they shouldn't be doing, because statistics can, and certainly has been doing for the last 30 or 40 years, build and analyse models in which, to the best of our ability, we try to combine information from two quite different sources. Data give us information, but scientific insight gives us information. And the process of inference is to take both of those sources of information in order to give as strong an evidence base as possible for the question that you're trying to answer. And clearly, if you collect bad data, you're liable to make bad inferences. And if you make bad scientific assumptions, if you do bad science, you're liable to make bad inferences. But I don't see those two things as being fundamentally different. We need both in order to make sharp inferences. So that brings us to an obvious question, which is data science anything other than doing science with data? Because it's hard to do, well, I've just said it's not hard to do science without data. You're a theoretician, but is data science anything more than just science with data, applied, experimental observational science? And of course it's interpreted to mean something rather different to that, rather more specific. And one of the things I want to challenge, and I hope nobody will think this is controversial, is that if you think that more data means more information, then you are deluding yourself. Because in practice, it's very often the case that the more you acquire data, the less your acceptable quality threshold becomes for accepting that data. If you want 100 observations on a phenomenon, you can do a very controlled, tight experiment. If you want 1 million, you might have to settle for observational data. If you want 1 billion, you might have to scrape it off the web. And although there's no theorem to this effect, I think it's a plausible rule of thumb that volume is often acquired at the expense of quality. And of course, the person who famously allowed us as statisticians to claim that we could do the best job possible with small data sets by designing them very efficiently and cunningly was R.A. Fisher. So Wikipedia's definition of data science is the extraction of knowledge from data, blah, 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 blah. Right? And my definition of statistics is the extraction of knowledge from data. Right? So does that mean they're just the same thing? Well, in practice, no. Because the key thing for me about the difference between what people might have traditionally understood by the statistics discipline and what I think a lot of contemporary statisticians would consider themselves is that informatics plays an increasingly important part in being a statistical scientist. Okay, and it's the fact that the science is underpinned by both statistical expertise and computational expertise that I think is a reasonable working definition of when statistics becomes data science. It's when you have that, you're really pushing the boundaries, not just in the stats, but also in informatics. And critically, you're doing it in a context. Right? So the domain in which you're applying your knowledge, to me, is fundamentally important because of that earlier triangle. That if you try to get context-free inferences, then as far as I'm concerned, you're not doing data science, you're doing data technology. And there's nothing wrong with that, as long as that's what you recognise that it is. Now, what changed in the first decade of this millennium in the world of what we might call biostatistics was that I coincidentally started editing a new journal called Biostatistics, and we noticed that the submissions to the journal over time started to show a very strong pattern. And this is a very crude piece of data analysis. I simply extracted from the first 10 volumes the proportion of papers that had the word genetics or genomics in its title. And from being a tiny, tiny fraction of papers in the volume 1, it became more than a third of them in volume 9 and dipped slightly in volume 10. And very roughly speaking, that was the time when all of the dry biology revolution was really accelerating, and there were interesting statistical challenges to saying, how do you take that raw biological material through these fancy machines into data that you can reliably analyse? And in terms of my metaphor, metaphors get less elegant the more complicated they become, but what it seemed to me was that the difference between traditional experimentation, where you do an experiment in the lab and you write the number 3.7 in your lab book, and modern biology, was that there are some serious intellectual challenges, including statistical challenges, to how you go from the biological raw material to analysable data. And I like to think of that as upstream bioinformatics. And that's why, you know, some people who call themselves data scientists, I think, are predominantly in this part of the triangle. They're very rarely down in this part where they're actually using subject-specific scientific theory to guide their conclusions. So if we as statisticians want to join the data science party, because it's obviously a very big party and a very wealthy party, so we do want to join it, I think the thing that remains our USP in a way is our use of probability theory in two contrasting ways. One is that we acknowledge uncertainty in our data by building stochastic models, and we're not the only people who build stochastic models, but it's absolutely core to what we do. If a model doesn't have a random variable in it, it's not a statistical model. But we also use probability in our conclusions. We use probabilistic inference in order to express uncertainty in our conclusions. And we may quibble about the precise way we do that, but I don't think we would disagree in any fundamentally important way that probability is the right way to formalise and measure uncertainty. Critically, as I hinted in my pitch of Ari Fisher, we have this strong tradition that design matters, but perhaps not as strong as it was before the computer revolution. I think one of the ironic downsides of the computer revolution in statistics is an increasing intellectual focus on models and algorithms at the expense of study designs. And I think, most importantly of all, that context matters. That when you're a biostatistician, you are not approaching a set of numbers in the same way that you would if you had been a financial statistician presented with the same Excel spreadsheet. The context is different, and that affects how you approach the problem. But what can we learn? We've got to be a bit humble, because one of the things that through most of my career that was pumped into me was that the end point of your research was a published article. And I don't think that's true anymore. Okay, minimally, I think the end point in a modern piece of statistical research is almost always a piece of software which, through things like R and Python and various other utilities, you want to disseminate to the world at large. And if people can't implement your methodology, they tend to be less impressed by it, however elegant it is theoretically. And that, of course, brings us into the much wider than statistical, but it includes statistical issues, science-wide debate of how we ensure that scientific results are reproducible. And there are many different definitions of reproducibility, but minimally, if I take a set of data and run it through a piece of software and get an answer, somebody else should be able to run the same piece of data through the same software and get the same answer. And even that, as you know, isn't always true, but you would like that to be a minimal standard. Okay, so that was really very much about bioinformatics, and the thing that seems to me to have grown up in the current millennium very strongly on its tail is doing the same thing for population health as was previously done at molecular health. And in practice, that actually seems to me to also indicate a change in the type of questions you're trying to answer, that a lot of population health questions are not so much about understanding fundamental processes as they are about predicting what is happening and what is going to happen to a community in terms of their collective health. I mean, it doesn't have to be all that way, but there's a balance of shift towards prediction rather than estimation or testing. And of course, prediction is one thing that the informaticians, and in particular the machine learners, are very good at. But I would like to argue that context is still helpful, so I just want to take you through two case studies, one UK-based, one overseas. And the UK-based one is the problem of looking in a population at risk of kidney failure for people whose kidneys do seem to be failing and who might need referral to specialist care for treatment. And there's an indirect proxy for somebody's kidney function called serum creatinine, which is a blood chemistry measurement. And clinicians over the years have turned this into an index, and some of you will see hiding there, doubtless a regression model with some point estimates. These are not claimed to be physical constants, but for better or for worse, this is what clinicians do if you are a kidney patient. They calculate your glomerular filtration rate, and very honestly they put an E in front of it because it's an estimate. It's actually quite a noisy estimate, but it's the best clinical measurement that's available routinely in the clinic. And the reason why this is an interesting prediction problem is that kidney failure can be asymptomatic for many years. And if you can identify early on that somebody's kidneys are on track for failing, you can intervene. In the first instance, by controlling their blood pressure. In the second instance, by getting them ready for dialysis or transplantation. And you can't reverse most kidney conditions, but what you can do is slow their rate of progression, which is a very useful thing to do. Now, this is the kind of system that was available in Salford in 2003, city in the northwest of England, and I think is increasingly available in big health trusts and groups of health trusts, whereby all the clinical data is stored in a form where, in principle, you can access it, so that you can interrogate in effectively real time what the state of the clinical system is, and you can build predictive models to answer whatever question it is the healthcare researchers want you to ask. And this is very much core to Health Data Research UK's business, who pay 40% of my salary at the moment, and some of you will know that there's currently a call out from Health Data Research UK to set up what they call digital innovation hubs, to try to mimic essentially what Salford did in 2003 in an interconnected way around the country. But basically, if you're interested in kidney progression, you can get data from all the patients in Salford, and here's data from just one patient. And you can see what I mean in saying the assay is noisy, but equally you can see that for reasons I can't explain from this diagram, this person's kidney function was on a modest increase for a while, and then it changed. And it may or may not have flattened out. Time will tell. That's up to February this year. Now, there's a specific question lurking behind data like that, which is, should this patient be alerted to the fact that they appear to be suffering from incipient kidney failure and should be referred to secondary care? And the clinical guidelines in the UK are that if the clinician thinks they're losing 5% of kidney function per year, they should be referred to secondary care. So you can turn that into a statistical problem by taking a response variable, which is log transformed EGFR. We know that kidney function depends on age and sex and also history, which we're going to capture by an initial value when the patient first comes into the system. And we're going to build a stochastic model within which what we want to do is make a predictive inference about the current derivative of log GFR, the true kidney function. And if there's a high probability that that's less than minus 0.05, we would flag a warning to the clinician. So the data are noisy not only within patients but between patients, but there is an underlying trend, and if you can just see a kink there, you're correct. There is an acceleration point at about 60 years old in the natural loss of kidney function. Now you build your model, and slides like this are never much fun for the audience, but basically it's a regression model, a fairly simple regression model, with a random intercept to recognise that we do not know much about the patient's prehistory, and so they'll come in at varying levels of kidney function. It's a noisy assay, so we certainly want a Z-term, or we will seriously overestimate positive and negative derivatives. And we have a differentiable stochastic process W, and it's the derivative of that process that we're trying to predict. And so as the data come in, every 24 hours, if there's a new kidney measurement, we update our predictions. Here are a set of traces from our data set of 23,000 patients, and we're basically trying to get people like this as early as possible. This person's probably already not in great shape. This person looked like not in great shape, but actually had a recovery. And you can see you get various different sorts of dynamics. And if you actually fit the underlying smooth trajectory, you can see that the algorithm decides quite a lot of what you see there is noise. And if you turn it into, predictions, you find that I've lost a slide. And the next slide was going to turn these point predictions into probabilistic predictions that the current derivative was less than minus 0.05. So, not a good look, that. Apologies. I was, as you can guess, doing these slides today, and I managed to miss one out. It's lurking somewhere, but I'm not going to look for it. Okay. Now, this was going to be a little interlude, but I know that the chair wants to keep me to time, so I'll simply invite you to write down that web address and go and have a look at it, because the idea of what I've shown you in time also works in space-time. You can have a spatial temporal stochastic process for the rate of disease presentations of anything you're interested in, and you can run a predictive algorithm, and you can update maps of current rates of presentation. And although it's extremely difficult, in my experience, to persuade anybody to give me finely resolved individual human health data in real time, the vets don't have that problem. And if you go to this website and just run it on your phone or your laptop for a couple of minutes, things will pop up. And they are real animals seeing real vets being treated. And that's all going on at the University of Liverpool. And we're, up in Lancaster, we're working with Liverpool to build predictive algorithms of the kind I've just indicated, but in spatial temporal setting, so that we can actually distinguish chance occurrences from actual indications that something unusual is happening. So I commend that website to you. But what I want to do next, and not just because I'm close to Keppel Street, is suggest that really high-tech informatics solutions to public health problems are as relevant to the developing world as they are to the developed world. This is an epidemiologist on a field trip gathering data, and he may not have a car, but he's got a mobile phone in his pocket. And he's interested in looking at where there are high prevalence patches of a debilitating disease, onchocerciasis, popularly known as river blindness, which is being treated Africa-wide by drugs donated by Merck, and these are protected drugs. And the policy is to simply give everybody who's in an at-risk area the drug, okay? And that was working quite well for a number of years until it was discovered that a small number of people, several hundred out of several million, suffered serious, occasionally fatal reactions to what was presumed to be a safe drug. And by looking at them, the unfortunates who died post-mortem, and taking more blood samples and so on, it was found that the people who were having these serious adverse reactions were people who not only were at risk of river blindness, but they were heavily infected with a second parasite which causes a less serious disease called loiasis, and there was some kind of antagonistic reaction that was set up, and when you see the numbers that we're talking about, some of these people had 100,000 parasites per mil of blood, and as I understand it, the drug was very effective at killing the parasites, but they were in such high numbers that they actually caused little blocks in the the fine blood canals. And anyway, for whatever reason, this is a serious problem, and it was an impediment to continuation of the river blindness control program. So the first solution was to go out Africa-wide and map the prevalence of lower, and after appropriately nuanced arguments from a range of disciplines and a range of backgrounds, WHO adopted a policy that by the instrument they were using at the time, which was quick and easy to use in the field, they would define communities to be safe for mass distribution if the local prevalence of lower was less than 40%, and on that basis they drew this map where blue is safe, red is dangerous, and cream is don't know. But that's what you might call a proxy for the real problem, because the argument is that if we're worried about people who've got high levels of infestation, they're more likely to be found where prevalence is high. And an obvious question is, how much better could you do if you could collect individual level data on levels of infection? And so instead of defining a community to be safe if it had a low prevalence, you'd say a community is safe if the proportion of highly infected individuals is small. And you can, if you wish, apply level 101 statistics to say, okay, if I can measure infection levels in the blood, I just turn those into a binary, yes, no, for whether they have or haven't got at least 20,000, say. And that's not my number, that's their number. And you can do a binomial inference. But that's not very efficient when you're dealing with very, very small probabilities. Okay? Your relative error could really be quite large. We collected, that's the royal we acquired data that people like the gentleman on the motorbike had collected at great effort from villages around several quite distant parts of sub-Saharan Africa, within which for each person tested we had the actual quantitative measure of their lower infection. And when we analyse the data from different villages, we see a great uniformity of shape in the resulting cumulative distributions. We see a great variation in the intercept, going from about, in these data sets, 0.6, these 5 villages, it goes right down to 0 in some, from 6 to 0.9 and a bit. And happily, the one that has very low prevalence, mostly zeros, also has a very short tail, and it can kind of convince you that you've got a parametric model in which there's a correlation between how heavily infected people are in a community, on average, and what proportion of them are infected. So what that means is that you can actually use binary data to predict the proportion of people who are highly infected. It's a bold prediction because it relies critically on you getting the right model for the tail of the distribution. So you would do it, you can do it, and we did do it, but you would inevitably be a little wary of the conclusion making predictions out in the tail of a parametric distributional model. This slide just shows you that the idea is sound, in that these are the empirical correlations between the random effects associated with prevalence and level of intensity, and you can see it's pretty strong correlation. But what you would really like is to have more individual level data. So how are we going to collect that individual level data? What we're going to do, or what we'd like to do, is say when we go into a community, we calculate, we gather some data, we're defining an at-risk individual to be somebody who's got more than 20,000 microfilariae per mil of blood, and what we really like to make is a probability statement. And if we can do this easily in real time, we can do it sequentially. So you can go into a village and you can keep sampling until that predicted probability is as close to 1 or 0 as you want, depending on how risk averse you are. But you can't do that in the field with traditional microscopy. What you can do it with is this device here. And this is a prototype of a device called the Lowerscope, and it's yet another application of the mobile phone, in which basically the mobile phone receives the image of a blood spot from the microscope piece. It then takes a movie, and it analyses the level of movement in the movie, and that has been calibrated back in the lab against the number of parasites per mil. And it calibrates really very well indeed. And with that device, it's portable, you don't need to train people to use it beyond about half an hour, and the prediction algorithm can be hardwired. So you can run it in the communities, and as long as you're getting predicted probabilities that are 0.3, 0.9, 0.7, you keep going, and if the probability goes up to an acceptable level near 1, you do this, and if the probability goes up to down to an unacceptable level near 0, you don't do it. And it's a slightly frivolous remark, but what I like about it is that the big ethical debate is what's an acceptable risk threshold. And it allows the statistician to say, if you really have a 0 risk threshold, you can still use our methods, it's just you will inevitably sample everybody, and then you'll have a 0 error. But there's a meeting in Brazzaville the week after next, which sadly I can't go to, at which they're attempting to reach consensus on this, because at the moment this is a very contentious proposition, and there is quite a strong lobby to say that if you think somebody with more than 20,000 parasites per mil is at risk of a bad thing happening to them, you shouldn't give them the pills. And that's a laudable thought, but not really sustainable if you want to treat a substantial part of the population of sub-Saharan Africa. So that really brings me to the end, and it makes my metaphor more complicated and less elegant still, because the scientists essentially are all working up here, and when they think they've understood a process, they could go home. But what's increasingly important, I think, in modern public health is what happens downstream of all that. So an inference doesn't actually tell you what to do. It provides an evidence base. And to turn that evidence base into decisions, you need to communicate quantitative information, which might not just be numbers, it might be time series, it might be maps, it might be moving images, into a form that you can visualize and communicate to non-specialists who can actually make it routinely part of their work, and it would be no more mysterious to them than a sphygmometer for measuring blood pressure. And again, I think there's some interesting intellectual work there, not just mathematical and statistical, but psychological and social, in terms of what kinds of dissemination of rational scientific evidence can be communicated to the general public or to the general profession of health care services in a way that promotes good rather than bad decisions. It's way outside my area of expertise, but I do think it's at least as important in population health as all this stuff is in hard biology. Thank you.